25 ppm. So the penalty is some function of it. It could be a linear function, it could be a quadratic function, it could even be an exponential function. Most likely it could be an exponential function, right? Because nobody wants to put a linear penalty on you because, okay, now for our analysis we're going to assume a linear function just for simplicity. Now of course, so now you might say, well, okay, so then design the product, design this whole operation so that C is basically 0. Or what's the problem with that? Sorry?
You always have something.
Well, you can over-design the system. You can over-design the, what it means is that you have your actual plant and after that you put a scrubber in. And that's how it's really done, right? You always have some exhaust and then you put a scrubber to further reduce that C. So you over-design the scrubber so that your concentration for all practical purposes will be 0. Or design it to be 1 ppm. Is that a good idea? Well, I mean, no, your production is whatever it is. The scrubber is designed to handle that production. Cost of what? The cost of scrubber will go up, right? So, the cost of scrubbing is obviously going to also be a function of C minus C star.
Damn, so companies do that?
Sorry?
So companies do that? They're like, oh, we'll just take a hit and take penalty over getting like a scrubber?
Well, it's not like you think like that. It actually is going to be a function of C star.
They probably do that though.
It's not that they intentionally do it, right? It's not like they are telling you. It's like.
But they rather.
It's the same thing. When you design a traffic intersection, are you going to design it so that there are absolutely no deaths ever?
Well, no, I wasn't talking about lights. I was talking
Same
about
situation. Every case, you have no choice but to design it in a way that is safe while fully noting that you can never design anything to be 100% safe. Because if you do that, then what will happen? It will in turn impact something else in a negative way. That's what optimization is. That impact could be either direct or it could be indirect. It could be through money or it could be something even more direct. Like if you design traffic to be 100% safe, what's going to happen? Sorry?
No traffic.
Well, we have unlimited traffic or no traffic. Yeah, you don't let anybody drive. Or unlimited traffic because there'll be just, everything will be jammed everywhere, right? You will not be able to go from place to place to. Or make the speed limits to be 20 miles an hour, right? You remove all possible deaths from the system. What is the penalty? Penalties you don't get anywhere, right? So yeah, so these kinds of optimization are inherent in every field. Okay, it's not just chemical engineering. And reality, if you look into it in details, you will see that there is actually a cost per individual assigned for these kinds of optimizations. Not for, of course, chemical engineering, because people don't die from ammonia exposure, at least not in the short term. But in traffic accidents cases, there is actually a value. I don't know what that value is. You can look into it. Optimization. But anyway, the cost of scrubbing, so the cost of scrubbing is going to be dependent on C star. And let's just say that it is equal to, for simplicity, alpha over C star. Okay? Or it could be, let's say, yeah, so as C star goes to 0, this cost basically goes to infinity. Right? It's probably not a great approximation, but sorry? Oh, sorry, alpha over C. The C star is the target. Yeah, C star, sorry, alpha over whatever is the C, what we are designing. We want to figure out how should we design the system. What should be the value of this concentration that we're designing here? And let's just call that to be C star. Okay? So we cannot design it for 0, we cannot design it for 25 ppm. We're designing the system to reach certain concentration. And it will be between 0 and 25, obviously, right? Hopefully. But like you say, somebody might decide, I'm going to pay the penalty, because the penalty terms might be. But we think that C star should range from greater than 0, less than 25. Okay? Although if the penalty is very strong, it's certainly possible that the optimum may be larger than C star, but we prevent that, okay? Alright, so the cost of scrubbing is alpha over C. and C star is the most likely value. Okay, so this is an optimization problem. And let's for simplicity say that the penalty is some B, beta, times C minus Cs. Okay?
Wasn't the penalty F, C minus CS?
Yeah, some function. Well, because F is just one arbitrary function. Now I'm just saying it's a linear function. Okay? All right, so now therefore your penalty, total penalty, so your total costs is equal to alpha over C plus, well actually no, we are not going to design greater than 0, we're going to design greater than 1. Right? Because we know that 1 over C behaves very poorly around 0. So we don't want to design for C star. So C star has to be greater than 1. Right? We already know that it will not be a. Okay, so alpha over C plus beta C minus C star. Okay? So C minus C star. CS. So let me again clarify. C is the actual concentration. So I should call it C. C star equals to the target obtained by optimization. So our goal is to calculate C star, right? Because we are going to calculate C star today, and then we're going to go to the designers and tell them this is what you should aim for. Does it make sense? All right. So this is, sorry? No, so C star, our target is going to be between 1 and 25. Okay. All right, so this is the cost, but this cost obviously depends upon C. And that's unpredictable because C, we don't know what C is. Right? Yeah.
Couldn't you just solve the minimum requirement greater than equals 0?
No, because not all values of C are equally likely.
But you can put in this is what your design is though, right?
No, because they're two separate designs. When you're designing the equipment, there's always inherent unpredictability after doing your design. So you're designing, so you're doing this design, right? You design to achieve a target. But then something in the system will change, so what you're getting out will not be the target. Otherwise, you can just design for 25 and everything is good, you go home. Yeah.
But, so isn't cost of scrubbing and cost of different designs of the scrubbers?
Sorry?
Isn't the cost of scrubbing and cost of different designs of the scrubbers?
It is. You could say, well, you could design, think of this entire plant as the actual cost of the plant plus the cost of the scrubber.
Right, is that, so you're designing for specific C, so why don't you just optimize?
Because you could design for that, but then even after the designing, in reality, the value would be different.
Right, so your penalties don't change, but your design, I mean, your cost of scrubbing won't change.
No, that's right. But still the question is, what should be the target in that design? If you target 25,
Well, you find for the target by solving for the.
but then there might be, you may have to pay penalty lots of times.
Right, but that's the target.
No, but that's the point. If you design for around 10, you may never have to pay penalty. So what is better, 10 or 25?
So you're playing one hole, I think you always like to
Well, we don't know that. That's why we're doing that's why we do this calculation.
fuck up, yeah.
You just let me go through it and you'll understand. Yeah, we need that. So that's what, so what we do now is we say, okay, multiply this by probability distribution of C, okay, integrate that, and optimize that. Yeah.
Sorry, quick question.
Yeah.
If C is less than CS, would that whole term just go to 0 then?
So that's a good question, yes. So this is penalty only if C is greater than CS. Of course, otherwise there is no penalty. Yeah. So it's a step function. Okay, you don't get money back if it's lower than CS. All right? Sorry?
It's not a step function, it just isn't defined below.
Yeah. Basically, it is 0 below that and it is linear above that. Yeah. All right. So this is the cost which you can then optimize, right? Does it make sense? And this limits, of course, are going to be C min to C max.
I don't understand why this multiplied by the probability of C solves all those problems.
Because this will tell, because we don't know what C we are going to get.
What is
I can just multiply the other expression just by probability of C, just have it sort out.
Which expression should we multiply by probability of C?
No, just multiply the expression you had before for the cost by the probability of the C being any specific value.
Because this
what's the formula for it?
This is the actual cost. This is like the NPV, where the variable is unknown. This is sort of like the NPV as a function of C. Right? And you don't know that NPV. So you essentially, find out the most likely value of that, and that's what you minimize. Make sense?
What is P of C?
So
What
P is
function?
a C.
How do you know that? What is that is?
This, see, now we have to talk about how do we know this.
Oh.
So to know this accurately, what do you need to know? You need to know, basically, yeah, you can do a simulation of your entire plant, a dynamic simulation, where you look at all different inputs, outputs, you change them randomly, and from there you will see how C changes. Because C is like control. You guys have taken control? So anytime, so you can design a system, right? You can design a system for whatever you want to be. Maybe that's why you guys are having problems understanding this, because you haven't taken control. So you can design a system, right? You can design a reactor. Like you're doing reactor design, right? You can design the reactor to achieve a target concentration, right? But that design depends on a lot of variables. Some variables, some like rate constant, which in turn depends upon temperature. Rate constant depends upon the quality of the catalyst. It depends on the packing. It depends on the degree of mixing. It depends whether there are some stagnation zones or not. It depends on heat transfer, mass transfer limitations. It depends upon, I can keep going till the end of the period, and I may not be able to cover all possible ways through which deviations might occur in your design. Right? We do not know what will lead to the deviation, but we do know that there will be deviations. So this probability distribution function represents that you design your system around some set point, but in reality you will never get that set point. You will always get variations around that. Now the purpose of control is to bring you back to the set point.